Hi, my name is Manish Gupta, and in this video, I'm going to talk about EMU, which is the foundation model for multimodal generation. So what can EMU do? Well, EMU can be used for image captioning. So the input is basically this image, and then there is a text prompt. The image shows a photo of, and this is the kind of caption that EMU can generate. It can also do image question answering. So given this image and a question, it can generate a very accurate and crisp answer. Okay. It can be also used for in-context completion. So the input prompt could be this. So essentially, an image, and then there's a chinchilla image. There are 3 pandas, and then another image. And then you ask EMU, or other, it is sort of implied that EMU should predict what is there in the image. It basically says there is a Godzilla. Right? Similarly, you can have another image and then, say this is the first image, this is the second image. And then you can say the animal in the first image surrounded with the plant in the second image and can actually generate an image, right? Of course, uh, corresponding to this animal and surrounded by the plant in the second image, right? It can also do summarization, or rather it can also take several images and then sort of describe all the images. So it can understand the larger pieces of in context as well, or rather larger pieces of context as well. So it can say, you can say this is the first image, second image, third image, fourth image, describe all images. It nicely describes each of those images one by one. Okay. Further, you can also use it for image to image tasks. For example, image blending, so to say. So you can basically give these 2 images as input, and then sort of it is implied that you should blend these 2 images and create a blended image. So these are like blended image. A hybrid between a cat and a tiger with the texture and the stripes like the tiger. Okay. And then you could also do text to image. So you could basically say that, hey, here is the text. An elder man is playing guitar while on canvas, impressionism. And these are the kind of images that it can generate, EMU can generate, right? So it is basically a multimodal generative model. So it can generate text, it can generate images also. Video question answering. So you can actually give a video and then ask a question, and then it can come up with an answer. Similarly, another video, ask a question, and then can come up with an answer. Okay. You can also give, like, say, recipe videos and then say, step by step describe the cooking recipe shown in the video, and sort of gives you step by step understanding of the recipe. You can use it as a multimodal assistant. So essentially, let's say you gave some text and then an image, another text, and then it can actually reason over the image and the previous text and give you an accurate answer. Similarly, you could basically give this kind of an image and then say, explain this meme to me. It nicely explains that meme. And as I described earlier, you could do image blending. So here, these are like sort of hybrids in between these 2 images and so on for the other examples also. Right? You can also do this with paintings. Take 2 paintings and ask it to create some sort of hybrid painting, blended image blending, basically. Right? You can do multi-turn dialogue. So for example, you can show this picture and then ask what are the things I should be cautious about when I visit here. And it comes up with a few things that you should be cautious about, whether wildlife, water quality, and so on, nicely step-by-step bullet points. And then you can say, do you have any suggestions about safety equipment? And again, it can give you suggestions about safety equipment like life jackets, first aid kit, communication devices, navigation equipment, and so on. And lastly, you can say, can you write a poem about the image? And it sort of generates a very interesting poem about the image. Yeah. So in context, text to image. Yeah. So basically, you can actually give several things like this text and then image, text and then image. And then you can give this text and then it gives this image, or gives this text and you can get that image. So an image which basically nicely illustrates what is mentioned in the text. Here is yet another interesting, powerful use of EMU. So you can give an image of this woman and then ask, tell me 8 books written by the woman and recommend one to me. It actually tells you that this woman is Agatha Christie and actually can correctly identify the 8 books that she wrote, as a nice list. Okay. So as you noticed, EMU is really awesome. So what does EMU's architecture look like? Right. So essentially, EMU is a multimodal generative model, which basically can both take image and text as input as well as output image and text. Okay. So therefore, to be able to take image and text as input, it must basically take the image, process it through some image encoder, and then pass it to a transformer model. So in fact, the generative model is actually Llama. So Llama basically takes the text inputs as well as um, image inputs. So image inputs in these open and close image tags, and then can generate text, or it can also generate images. It can also generate images. Okay. Now, so therefore, EMU is more like a large multimodal model. It's a large multimodal model. But typical large multimodal models have some drawbacks. So for example, typically they are trained on image text pairs or documents while overlooking videos, but there is so much to learn from videos, right? So EMU has been pre-trained on videos as well. Right? Typically, large multimodal models are trained with next text token prediction with a frozen vision encoder, right? So you have vision encoder and you have like text, and next text token prediction is what these large multimodal models do typically, right? But we will see in the next slide how EMU is pre-trained, right? And third, videos basically are completely ignored by these large multimodal models, although the frames and subtitles in these videos are actually richer than the common crawl corpus itself, which is like one of the largest corpora, which is sort of used for training the large multimodal model, the text part of the large multimodal models. Okay. So as I was describing, EMU's architecture basically consists of an encoder, image encoder, EVA clip encoder model. It also contains Llama, which acts as a sort of large language modeling, large language. So it basically is a decoder only transformer model, right? And then you can actually decode text tokens, or you can actually get some image tokens, which can then be decoded using stable diffusion decoder kind of model so as to generate an image. Okay. Now, on the input side, how do you encode text, encode images? So images, basically you take the input image, you pass through the EVA clip model, that's the encoder, but then you also pass it through this causal transformer. Okay. This causal transformer basically gives you a fixed size representation of the image. So fixed n size representation of the image. So the causal transformer takes the two-dimensional EVA clip encodings. So EVA clip still gives you a two-dimensional representation of the image, and then it converts it to n one-dimensional visual causal embeddings. Now, causal transformer, basically this piece is essentially a transformer decoder, of course, containing the three things: causal self-attention layer, cross-attention layer, and feed-forward layer. It accepts n randomly initialized embedding, n randomly initialized embeddings representing the, supposed to be representing the image, and then outputs, of course, transformed n representations, which actually represent the image. So these are the n things which basically are then passed to the passes input to the Llama transformer, right? The causal self-attention layer actually captures the causal dependency among the input latent embeddings. So it's basically a transformer decoder. So that's the causal part of the causal transformer. And then it also has a cross attention. The cross attention basically ensures that keys and values essentially come from the visual EVA clip embeddings. So keys and values actually come from there, and the queries are essentially the randomly initialized image token embeddings in that sense. Okay. So that's that, and then of course the cross attention computes the attention and transforms these queries. Okay. So now that we have understood the architecture, how is EMU trained? So EMU is trained, the input can be text or image token, as we discussed on the previous slide. So it is pre-trained by doing the following things. You convert all 2D signals to 1D signals. So basically, if it is text, of course, you retain the text as it is, but images or video frames are converted into one dimensions using causal transformer. The pre-training loss is cross entropy loss for discrete text tokens and L2 regression loss for visual embeddings, right? So this is the visual embeddings that are created, which are then taken by the stable diffusion model so as to decode the stuff. Okay. For pre-training, they basically make use of video data also, besides, of course, making use of the large image text pairs, interleaved image plus text data. They also make use of video text pairs in the WebWidth 10 million dataset, which is videos with text descriptions. And lastly, they make use of interleaved video and text data, which is basically videos with subtitles, videos with transcripts in that senses. Okay. So this is a nice large YouTube storyboard 1 billion data set. So practically they make use of several data sets: image text pairs, interleaved images, text data in MMC4, right? The multimodal C4 data set, right? And then WebWidth 10 million data set, and also YouTube storyboard 1 billion data set. They use Llama 13 billion as their multimodal large language model. They also use, that's that. They also use EVA02 clip, which is a 40-layer VIT model for image encoding. Their causal transformer contains 12 blocks. So overall, EMU has 14 billion parameters, right? So most of the parameters, of course, are in Llama, but then there are some parameters in the causal transformer and the EVA2 clip model. Okay. So for each video, so of course, images can be processed very easily. You basically pass that through the clip model, and whatever you obtain, I mean, the 2D representation is passed to the causal transformer so as to get a 1D representation, right? But for videos, you basically sample 8 frames and use them for pre-training. So after the pre-training is done in this way, using these 4 datasets, you basically do yet another round of fine-tuning the image decoder. So, all of these basically do not require image decoding, but the next round of pre-training basically involves, or other, you could call it fine-tuning, involves image decoder learning. So, and you do that using these 2 datasets, Lion Coco and Lion aesthetics dataset. To do this, you initialize the diffusion model with stable diffusion v1.5, and then you freeze everything else in EMO. So the visual encoder, multimodal LLM, the Llama model, the VAE in the diffusion model, and only the unit parameters inside this stable diffusion are updated. Even the VAE is sort of fixed. That's also frozen. Okay. Remember, stable diffusion essentially tries to do diffusion in the latent space. So first, it basically compresses the input using VAE, and then does stable diffusion, and then decompresses it, or sort of use the VA decoder so as to get the full-blown image, right? So once that is done, so this is step 1, pre-training. Second step, fine-tuning, and the third step is multimodal instruction tuning. In multimodal instruction tuning, they basically, of course, need instruction tuning datasets. So first, they start with language instructions from ShareGPT and Alpaca. Then they look at image text instructions from Lava. They take video instructions from VideoChat and VideoChat GPT. And while doing instruction tuning, they freeze all the parameters of the pre-trained EMU, only update the LoRa parameters, and LoRa parameters also around the self-attention layers of Llama. Okay. Vision encoder, they don't touch at all. So no LoRa parameters, and the visual encoder is frozen essentially. So vision parameters are not updated. Multimodal instruction tuning basically only updates the LoRa parameters that do around self-attention layers in Llama. Okay. So of course, for instruction tuning, you need some way of passing the instructions. So you pass a system message, and then user token, and then the instruction assistant, and then the answer. Okay, so that's basically, of course, the instruction essentially comes from these datasets. Answer also comes from, of course, these datasets themselves. Okay. So lastly, let's talk about how does EMU perform. So they evaluate performance on 3 different kinds of evaluation. So the first one is multimodal understanding evaluation, so which involves image tasks as well as video tasks. And in image tasks, you have several tasks like captioning, visual question answering, and so on, visual dialogue as well. And in video tasks, you basically again have video question answering mainly. Okay. And then the second kind of task is zero-shot text-to-image generation task. So you have text and you want to generate images. The third task is few-shot image and video question answering tasks. Okay. So remember, this is a zero-shot evaluation. This is a few-shot evaluation, the lower one. So in zero-shot evaluation, they compare with various models, MetaLM, Cosmos 1, Flamingo 9 billion, and so on. Right. And they have 4 variants of their EMU model: the standard EMU, the instruction-tuned EMU, and that's EMU-I. And then EMU star. EMU star is basically, it's like zero shot, but then they actually give, 2 examples from the task with images removed. So since images have been removed, it's more like 2 shot, but then since images have been removed, you can actually call it zero shot, right? In that sense. Okay. So that's that. So there are the 4 variants of EMU, and as you observe, typically the EMU instruct-tuned model does well across most of those tasks. Now, to be able to do this, essentially they do they actually prompt. They do the instruction-based, or rather they do the prompting for this model using multimodal chain of thought prompting. So first they ask the model to generate a descriptive caption for the visual content. So of course, these are image tasks, so there'll be visual content and input, video task, image, visual content and input. So they ask the model to generate a caption for these images. Then they provide the model both with the caption and a task-specific prompt in the second stage. Now, from a image generation perspective, they take text as input, generate images, and evaluate using the freshet image distance kind of measure. Lower the better, right? And what you observe is that while these models are unimodal in nature, they only generate images. GIL and EMU are multimodal in nature. And as you observe, EMU actually has a very low FID. Of course, this FID is not as low as some of these other unimodal generation models, but reasonable enough. Okay. Lastly, they also do few shot image generation, image and video question answering using 2 shot, 4 shot, 8 shot, and on 4 different data sets. And as you observe, EMU actually outperforms Cosmos instruction tune Cosmos 1 and Flamingo 9 billion, right, across most of these settings effectively. Okay, so in summary, in this video, I talked about EMU, which is a large multimodal model trained with a unified autoregressive objective of predicting the next element. And the next element need not be text only. It could be both text as well as images. Right? And it has been shown to work so well on diverse multimodal tasks like image captioning, image question answering, video question answering, in context text and image generation, text to image generation, image blending, and so on. OK, so that's it for this video. Hope you like the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.